Hello, and thank you for coming to my talk on general path integrals and stable SDEs. This is joint work that I've done with Leif Döring from University of Mannheim and Andreas Ciprianu from Bath University. I've put here some references, what you can pause the video to look at. This is the past work on which we've based some of our work, and I'm going to reference later on as well some of the theory that exists in these works of Engelbert and Schmidt from 81 and later a couple of papers from Zanzotto. My talk has three sections. The first is on stable SDEs, what they are, a bit of background, especially on what stable process is, because I expect that's what most people here will be least familiar with. So the Brownian motion you will be very familiar with, I'm sure. It has many useful properties, which is why it appears just everywhere in any work with stochastic processes. And we shall particularly be interested in two of those properties. The first is self-similarity. For the Brownian motion, self-similarity is described with a parameter, either 2 or 1/2. Just one is one over the other, but it's the same self-similarity. And it describes the scaling. You can scale a Brownian motion in time and in space and end up with a new process that is, of course, pathwise a different process, but has the same law as the original Brownian motion before you scaled it. If that property is maintained, but the rest of the process is generalized, can have other behavior, then we get what's called a self-similar process. Most often, the Markov property of Brownian motion is also maintained, and one obtains a self-similar Markov process. We want to maintain as well the Levy property of the Brownian motion, and that's what's called a stable process. It's self-similar, like the Brownian motion is, but now with a more general index alpha that can be actually anywhere between 0 and 2. And the Levy property as well. So Levy is just Markov and also homogeneous in space. A stable process doesn't maintain continuous paths. It is significantly different from the Brownian motion, but as we will see in a moment, it also is similar in some ways, maintains some properties. Self-similarity is the key property which relates path integrals to SDE solutions. That's what this talk is about, via a particular time change. If you take a stable process, define an increasing process that's also random, depends on the path of the original process, and use that as the time scale for your original, you obtain a new process. And the idea is somehow that mimics both the time and simultaneously the space scaling of the self-similarity property, and one obtains a new process that's not quite stable, actually becomes a solution to a stable SDE. Self-similarity is the key to that. So why Levy? Well, a Levy self-similar process, that is a stable process, has a particular jump measure, or equivalently a compensator. You can go from one to the other, 1 to 1, that has a very nice form. So the form of the jump measure of a stable process is used then in proving this relationship, the connection between path integrals and SDE solutions. There's no other reason, to my knowledge, why similar work couldn't be done for self-similar Markov processes. Markov property is pretty much necessary, but self-similarity is the key. The Levy property otherwise is not necessarily used, but the work we've done is just for stable processes, and although I don't know of any reason it couldn't be done for others, I also wouldn't know exactly how to go about doing that. Worth mentioning, there are two different regimes within stable processes. The first, when alpha is between 1 and 2, the index of self-similarity, alpha. Your process looks similar to a Brownian motion. The paths are discontinuous, that's a big difference, but the process is point recurrent, has finite mean, has local times, so it hits points. These are all properties it shares with the Brownian motion, and they're all useful in proving things relating to this connection. And that's the work of Engelbert, Schmidt and Zanzotto. That's what they did. For alpha less than 1 and greater than 0, stable processes are transient, they have no moments, and they don't have local time, so they don't hit points. And all of these things make it harder to do the analysis, and that's what we had to work through. So then we can just very quickly define what a stable SDE is. So this is a lot of info, but it's what you will have seen before. A weak solution, we're only concerned with weak solutions, to a driftless stable SDE is a triple. X, stable process, Z, solution process, and curly P, a probability space. And the solution process Z has to satisfy this integral equation, where sigma, our choice of sigma, is non-negative and Borel measurable. So that's the integral driven by the stable process there. As an example, the trivial solution, when sigma is 0 at a particular point z, or initial point, then a solution exists which is just constant the whole time. And the issue that Engelbert, Schmidt and Zanzotto first approached, and that we will approach for more stable processes, is that not every choice of sigma allows a solution, and some choices of sigma allow only the trivial or only non-trivial, things like that. These are different regimes that can be explored in terms of deterministic integral tests. Now let's talk about these integral tests. First, one from Engelbert, Schmidt and Zanzotto. For alpha in between 1 and 2, inclusive of 2. 2 being the Brownian motion, and like I said, between 1 and 2 being processes that look similar. Sigma is measurable, non-negative. Then the following equivalence holds. First, there exists a non-trivial weak solution to our stable SDE, if and only if. Second, this integral test holds over a set U which contains this initial point. This initial point of the solution has to be in the set U. The integral test is sigma to the minus alpha. Just has to be integrable on the set U. The key here is the question of which sets are hit immediately. So for the Brownian motion and alpha greater than 1 stable processes, all Borel sets which have Z in the closure are hit immediately by any solution process, solution to this SDE, which starts at Z. So essentially what this integral test is saying is that around the point Z, which is everywhere that you immediately hit, there's some like safe behavior of sigma. That is the intuitive idea. Sigma behaves nicely around the initial point Z. So we extended this, well, not really extended, more like reflected or mimicked this result, but for a different class of stable processes, that's alpha less than 1. So these are the transient processes which don't hit points. And the result we got is essentially the same, but just with a different condition that relies or depends upon the different behavior of the alpha less than 1 stable process. So again, an equivalence between existence of a non-trivial weak solution to this SDE, but now the integral test is slightly different. We have an integral against U, our open set, but now minus some set B, which I've called thin. I'll explain that in a second. But against this also different polynomial factor, y to the alpha minus 1. This polynomial factor for alpha greater than 1 obviously also doesn't have such an impact on the integral test. The thin set B is really the major difference here. So the definition of thin at a point is it's any set which is only hit at positive time. It's not hit at infinitesimally small times. And what I explained before is that actually for the alpha greater than 1, and like the Brownian motion, any set which has the point in its closure will be hit immediately, will be hit at infinitesimally small times. For alpha less than 1, that's not true. It's possible that this set B contains Z in its closure, so it kind of can get arbitrarily close. But it's still not hit until some positive time, or possibly not hit at all. That subtlety means that it has to appear in the integral test, and in a sense it does appear in the integral test of the process before. It's just it appears in an arbitrary way. You can choose U small enough, your open set, such that it doesn't contain the thin set for any choice of thin set. In my last minute and a half, or perhaps just minute, I'm going to talk very briefly about some solution properties. The first is explosion. It's possible to define this concept of whether or not a solution to the SDE explodes. We define explosion time as the first time in which the solution leaves the real line. For a regular stable process, it just stays there, like the Brownian motion, stays in the real line for all time. So this will be infinity. But for a solution process, it's not necessarily true. The time change representation that I mentioned allows this particular definition, or not definition, but equivalent representation of the explosion time. It's an integral from time 0 to time infinity over sigma applied to a stable process, sigma to the minus alpha. Once one has this integral representation, one can define if and only if conditions for explosion, that is zeta being finite with positive probability or with probability 1. The conditions are integral tests, they're deterministic. And that's using the same kind of techniques as we use to derive the integral tests for existence of solutions at all. I wanted to talk about something else, but I don't have time for that. So thank you very much.